Welcome to The Explainer. Today, we're jumping right into the brilliant techniques that are making these giant AI models smaller, smarter, and, honestly, a whole lot more accessible for everyone. We are talking about the fine-tuning revolution.
So, let's kick things off with a huge question. Imagine you've got this incredibly powerful general-purpose AI. It knows pretty much everything on the internet. But you need it to be a specialist, maybe a hyper-efficient legal assistant, or an expert at summarizing medical documents. How in the world do you do that?
Well, the answer isn't what you'd probably guess. It's not about brute force. It's not about just adding more and more power. Nope, it's about finesse. And it represents a complete shift in how we think about adapting these amazing models.
To really appreciate just how clever these new methods are, we first have to wrap our heads around the sheer scale of the problem they were designed to solve. The old way of doing things was, well, it was a bit of a mess.
The old method, what we call full fine-tuning, is kind of like trying to re-engineer an entire jet engine just to make it a little bit quieter. I mean, it updates every single one of the model's billions of parameters, and that takes a staggering amount of memory. Just look at this number, 80 gigabytes of VRAM, just to tune what we now consider a small model. That's way more computing power than most people or even small companies can get their hands on.
And it's really crucial we get the difference here. Pre-training, that's where the model builds its massive foundation of knowledge by basically reading a huge chunk of the internet. Fine-tuning, though, that's the next step. That's the specialization phase, where we take all that general knowledge and adapt it for one specific job. But here's the real kicker with that old brute force method. By being so aggressive, by updating everything just to learn one new thing, the model can actually overwrite and forget its original, powerful reasoning skills. This problem has a name that sounds just as bad as it is: catastrophic forgetting.
So, yeah, we clearly needed a better way. Something that could specialize these models without needing a supercomputer and without causing digital amnesia. And that challenge, right there, sparked this incredible wave of innovation called parameter-efficient fine-tuning, or PEFT. And it completely changed the game. I mean, just look at this timeline. The speed of progress here is just incredible. In just a handful of years, the AI community went from this hugely expensive, exclusive process to methods that are so efficient, they've basically put this power into the hands of developers everywhere.
So the first hero in our story is LoRA, which stands for low-rank adaptation. The idea behind LoRA was a total game changer. The theory was, hey, what if you don't need to change the entire model to teach it a new skill? Instead, you can just freeze the massive original model and train these tiny, super-efficient adapter layers on the side. Think of them like little adjustment knobs that can guide the model's behavior without messing with its core wire.
Then came the next big leap, QLoRA. It tackled that massive memory problem you can see right here. The absolute genius of QLoRA was to quantize the base model. That's a fancy way of saying it compresses all the information it holds down to a super efficient 4-bit format. This just slashed the memory footprint, and suddenly it was possible to tune those enormous 70 billion parameter models on a single consumer-grade GPU. Wild!
But even with all this new efficiency, there was still this little performance gap between these smart new methods and the old brute force way. And that's where DoRA came in. It closed that gap with a really clever trick. It decoupled the direction of a change from its magnitude. You can think of it like giving the model a separate compass to set its direction and a throttle to control its speed. It just allows for way more precise adjustments.
Okay, so now we can tune these models efficiently. Great. But that brings up a whole new question, right? How do we make sure the AI is actually helpful and harmless and, aligned with what we actually want it to do?
This is where alignment comes into play. See, supervised fine-tuning, or SFT, is great at teaching the model how to follow instructions, the right format, the right style. But alignment is all about teaching it what to say. It's about guiding it to be more helpful, to say no to harmful requests, and just generally behave in a way that we'd prefer.
And the cool thing is, we have all these modern ways to do alignment that are so much simpler now. Take DPO, for example. It just learns from paired data. You show it a chosen response versus a rejected one. Simple. But then you have something like KTO, which is awesome for businesses because it can learn from unpaired good and bad examples, like a big log of successful and unsuccessful customer service chat.
Of course, this isn't all just theory. It's all put into practice using some really powerful software libraries. You can think of these as the modern tuner's toolkit. You've got Unsloth, which is like the speed engine. It's built for pure velocity. Then there's TRL from Hugging Face, which is a super flexible toolkit perfect for playing around with the latest and greatest techniques.
And for anyone who needs perfect consistency, there's Axolotl, which makes sure every single training run is perfectly reproducible. So, we figured out how to refine the AI's behavior. But what about expanding its senses? I mean, this whole revolution doesn't just stop with text. The next great frontier is teaching AI to understand the world not just through words, but through sight and sound too.
A multimodal model is basically a partnership, a team-up of three key parts. First, you've got a specialized vision encoder that looks at an image and basically describes it using math. Then, a simple little connector acts like a translator, turning those image numbers into a language the main LLM can understand. And finally, the LLM backbone puts it all together, processing the text and the image info at the same time.
And here's a little peek at how it actually works under the hood. When you're feeding it data, you use this special little tag, an image token, that acts as a placeholder. It tells the language model exactly where to insert its understanding of the picture, seamlessly weaving sight and text together. It's pretty elegant.
This whole journey, from that brute force full tuning all the way to the finesse of things like QLoRA and these new multimodal models, it has fundamentally democratized AI development. It puts the power to create these highly specialized intelligent systems that can see and reason into the hands of more creators than ever before. So really, the only question left is the one right here. Now that we can adapt AI to any task, sight, or sound, what will we build next?